Hey, how's it going? Today our presentation is going to be over the chemistry of extracting and producing petrochemicals. And this is going to be brought to you by Kenneth, Dustin, Jacarius, and Alex. Now, when a lot of people think about the oil and gas industry, a lot of people think about, just pump jacks and oil rigs, just come to mind. But the truth of the matter is, there's a lot of chemistry that goes on behind the scenes that goes into, actually producing oil and natural gas from getting it out of the ground to actually, producing very useful products such as, plastics and adhesives and everything like that. So we're just going to go over a little bit of the chemistry makeup that goes into each sector of the oil and gas industry. So the first sector we're going to take a look at is the upstream sector, and this sector pretty much just includes the searching for potential underground crude oil and natural gas reservoirs and everything like that. It goes into into operating the wells and recovering and bringing the crude oil back up to the surface. And the next sector we're going to take a look at is the midstream sector, and this sector pretty much involves the transportation, either by pipeline, rail, barge, or oil tankers. It also includes the storage and the wholesale of marketing of the crude oil and refined petroleum products. And the last sector we're going to take a look at is the downstream sector, and this sector commonly refers to as the refining of petroleum and crude oil and the processing and purifying of the natural gas. Now, the first sector we're going to take a look at is the upstream sector. And basically, what goes on in the upstream sector is it pretty much just start off with the drilling process. When the oil and gas companies come out and they survey the land, and they find a reservoir deep within the ground. The first thing they're going to do is come out and set up a drilling rig, and this drilling rig is basically going to get us from point A on the surface all the way to point B, which is our touchdown point there in the reservoir. And once we get there, hopefully we'll extract the oil and natural gas. And now it seems pretty easy, pretty simple goal, just reach the underground formation. And we're gonna do this by using a huge drill bit to drill all the way through the formations and obtain the oil and natural gas. And here's just a picture of the drill bit we're gonna use. Just a standard mill tooth drill bit to go through these formations. It's an older one, but it's okay. Sounds pretty simple enough, but there's a lot of problems faced when drilling through these formations, and this is where a lot of the chemistry uh, practices are going to come into play. Some of the problems we're going to run into are problems such as the drill bit might get stuck, the drill might get too hot when it's drilling through the formations. We need to stabilize the wellbore. The further we go down into the earth, the more unstable those wellbores are going to be, depending on what type of fragile formations we might drill into as well. We need to get the shavings out of the wellbore. You can think of it like as a pencil sharpener. The more and more you sharpen like a pencil, those shavings, crowd the sharpener, and we need to get those out of there so the sharpener can work, more efficiently. The drill string also needs to be properly lubricated. We might run into certain hazards, such as like holes in the wellbore where we lose all of our circulation. We just call that lost circulation material. And another sector where a lot of chemistry runs deep is the contaminations that we run into from the formations that we drill into. And some of those formations may come from, anhydrite formations or gypsum formations. And those formations contain a lot of calcium cations. We might run into hard water contaminations, which contain a lot of magnesium cations. CO2, carbon dioxide contaminations, and even cement contaminations are more the common contaminations we run into on the drilling. And how are we going to solve these problems? Well, we're going to basically use a mud to help us solve some of those contamination problems. And basically, the mud we're going to be using is a non-Newtonian fluid, which is anywhere from 9 pounds per gallon to 18.5 pounds per gallon, which is a lot heavier than water, which is 8.33 pounds per gallon. And what the mud does is it controls the subsurface pressure, helps remove cuttings from the wellbore depending on the weight of it, and it helps maintain wellbore stability. And keep in mind, this isn't oil. We do drill with oil-based muds and water-based muds, but we haven't actually, gotten to the oil. This is added mud that we add to the drill string and pump down the wellbore up the analyst and back up to the drill string to help us actually get to the oil and natural gas reservoir. And we do this with the help of added chemicals that we call additives. And some of those additives are that we use more commonly on the drilling rig is barite, better known as barium sulfate, and we use that to weight the mud up. Hematite, it's an also weighting agent. It's a lot heavier than barite's iron oxide, which is at 5.0 specific gravity, I believe, and barite is at 4.2 specific gravity. So it's 4.2 times heavier than the weight of water. SAP is another common chemical we use on the drilling rig. Caustic soda, which is sodium hydroxide, soda ash, sodium carbonate, gypsum, calcium sulfate, and anhydrite has the same chemical composition pretty much as it has a lot of calcium, as I said earlier, in it. And here's just some pictures of the barite sacks right there on the drilling rig. You what's contaminated in our mud, and how do we know how we're going to treat our mud? Well, we're going to run a certain field tests on our drilling fluids. One of the most common tests that we got to run is the mud density test, which uses a mud balance, to find the mud weight of this mud that we're using. That's measured in pounds per gallon. Another test we got to run is a viscometer test, which tests for the plastic viscosity, yield point, and apparent viscosity of the mud. We also got to use that to test for the gel strengths as well, and that's measured, pounds per 100 feet squared. Another test we run on the mud is a filtration and cake thickness test, and that's using an API filtrate test, which stands for the American Petroleum Institute filtrate test. And this basically just tests pretty much just for the fluid loss that we are experiencing through our mud. And the most important thing about this is that we can't really lose any fluids through our wellbore, and this helps us determine exactly how much fluid we are losing down the hole. The pH test, which is pretty much the next most important test. Oh, they're all pretty important, really, but the pH test is what's special about it is that it tests for the alkalinities of the mud. And to give you an example of why we got to do that, basically what would happen is if we had a pH of less than 8 in our mud, microorganisms can multiply and they'll produce a lot of oxygen within the mud. And when they produce oxygen, that also corrodes the drill string, and that's not very good because the drill string, the annulus, the drill bit, those are very very expensive products, and we just can't have that being ruined. So in order to prevent that from happening, we got to keep the pH of our mud up above 10 at least to kill those microorganisms. We also look at the hardness of certain chemicals as well. And to give you an example, well, like the hardness elements such as like magnesium and calcium, if those precipitate out of the water, those precipitate at a certain pH, which is 10, and the hardness inhibits the swelling of clays and gels, and it'll be impossible to increase the viscosity of that mud, and it'll be impossible also to weight that mud up. So that's another reason we got to keep the pH at certain levels to help these control these problems such as magnesium and calcium. We also run a simple sand content test. Just measures how much sand we got in the wellbore. The retort liquid test just measures the fraction of oil, waters, and solids that we have in our mud. High temperature, high pressure test. That just stimulates wellbore conditions and just show it's a more extreme version of the filtrate test, just at higher temperatures. We also run a certain chemical analysis on our mud, and that just pretty much just tests for the alkalinities in the mud. And there's three basic alkalinities that we just test for. The first being the hydroxyl alkalinity, the carbonate alkalinity, and the bicarbonate alkalinity. And some of the factors that we measure for is the PM, what's known as the PM of the mud, and that's just a measurement of the number of milliliters it takes for N50 sulfuric acid that's needed to reduce the pH of 1 milliliter of pure mud to 8.3. The next measurement we test for is the PF of the mud, and this comes from the filtrate from our API filtrate test that we have collected in a graduated cylinder. And that's just a measurement of the number of milliliters that it takes the N50 sulfuric acid needed to reduce the pH of 1 milliliter of the filtrate to 8.3 as well. And the MF is another measurement we test for, and that's just a measurement of the total number of milliliters of N50 sulfuric acid that we need to further reduce the pH of 1 milliliter of filtrate to 4.3, and that's just a total measurement of these two alkalinities. Another important measure that we test for is the chloride, which is the salinity of the mud filtrate, and that's measured in milligrams per liter. And another important test to run is the hardness test, and it just tests for the total amount of hardness in the mud or the filtrate. Here on this slide, I just included some pictures of all the tests that we actually run on the drilling rig, just to give you a better idea of what we actually got to do. Here we have the first one we have the API filtrate test, and we just pretty much just put the mud in this canister, pressure it up with CO2, and we leave this running for 30 minutes, and we collect filtration here in this graduated cylinder, and we just use the results that we have from this test to further use on the other tests to get results from these other tests that we run. And here we have the pH, basic pH test. Right here is the HTHP test, high temperature, high pressure test. This is our viscometer that we run at 600 RPM, 300 RPM, and then bring it back down to 3 RPMs to test the gel strength. Here we have our basic mud balance here that we use to find the pounds per gallon of mud and funnel marsh funnel. I'm sorry, right here. Here's all the here's basically a mud kit that we use on the drilling rig, and this just pretty much just has everything on it. Introduced sulfuric acid, phenolphthalein, methylene blue test, everything. Just a little box to keep all your chemicals in. Here's the retort test that we put our mud in to actually get the percent solids, percent water, and percent oil content test. And also here's our sand test that we got to test the mud for as well. Just to give you a basic visual of what these tests actually look like. I just wanted to present, just basic outline of some of the contaminants that we might run into and pretty much just how to treat them. And here, we're also given their contaminant ion. So, gypsum, anhydrite, lime, cement, those substances have a lot of calcium in them. And basically, like one of the rules of thumb on the rig was pretty much just, anything that has calcium, just treat it with a carbonate element, such as sodium carbonate or sodium bicarb, I'm sorry, and then soda ash. And over here on this column over here, it's not really anything anybody needs to worry about, but it's just some of the calculations that go into of how much concentration, how many sacks and stuff like that we need to add for to get our pounds per barrel additive right. And hopefully it just gives you a little bit more uh, of an idea of what exactly goes on the rig. When it comes to mud engineering and drilling fluids engineering, a lot of work and art goes into you know trying to get the mud just right so it's ready to help get the wall and everything ready for production. A lot of people just think that drilling is just real uh, simple, I guess. Just drill a hole down to the touchdown point, like I said. But there's actually a lot of chemistry that goes on behind it, and basically without any of these processes, it'll be basically impossible uh, for there to be any sort of production of oil and natural gas from under the ground. And hopefully it just gives you a little bit more appreciation of what chemistry actually goes into the upstream production of petrochemicals. And hopefully if everything goes right, the mud engineer is good. He knows what he's doing. You hit the touchdown point with the where the reservoir is at, and then hopefully trip out of the pipe and get the oil ready for production and onto the midstream section.
Petrochemicals. At this point, we're going to take a look at the treatments and transportation of petrochemicals. Midstream. The petroleum industry has three major sectors: upstream, midstream, and downstream. Midstream, emphasizing on mid in its name, this sector is the middleman out of the other two. This process mainly focuses on transporting natural gases and crude oils. How midstream begins? Once crude oil and natural gas fields are discovered through upstream, it's the midstream process that focuses on transporting petrochemicals to a wide variety of companies, such as barge, railroad, trucking, and pipeline transports. Although midstream is a process of transporting, it still has processes that are similar to upstream and downstream. For example, midstream still correlates with upstream by working with wells and the specific type of wells which obtain the specific form of crude oil or natural gas. And downstream with its refining process to extract contaminants from the natural gases and oils. During upstream, natural gas and crude oil are transported together through a pipeline. In the process of extraction, these petrochemicals are not pure. They most likely have a form of contaminant. This leads to natural gas processing. It is the process of separating non-methane hydrocarbons such as benzene, ethanol, formaldehyde, and cyclohexene, along with fluids from raw natural gases to produce a pipeline quality of dry natural gas, which is suitable for transporting through pipelines to distribute to companies. Natural processing plants purify raw natural gases from common contaminants such as water, carbon dioxide, and hydrogen sulfide to create a byproduct suitable for transportation. Natural gas that comes from crude oil wells are called associated gas. Associated gas means natural gas that is above the crude oil when it's underground. Although natural gas can dissolve in the oil, therefore it is termed as a dissolved gas. There is another well that can obtain natural gas. It is called a condensate well. This means the well would have little or no crude oil, terming the gas as non-associated gas. Gas wells usually produce only raw natural gas. On the other hand, condensate wells produce raw natural gas along with lightweight hydrocarbons. These wells collect natural gases in different forms to be processed into byproducts. A process similar to natural gas processing is liquefied natural gas. Liquefied natural gas predominantly pertains to methane. It is easier to transport natural gas as a liquid than it is in a gas state, because it can avoid hazards and occupies far less volume if transported as a liquid. Although natural gas is colorless, non-toxic, and non-corrosive, it still has the high risk of flammability. Liquefaction involves the removal of components such as dust, acid gases, helium, water, and heavy hydrocarbons. If these components were not removed, it would make the downstream process more difficult. Once the contaminants are removed, the natural gas is condensed into a liquid by cooling it to a negative 260 degrees Fahrenheit. This achieves a higher reduction in volume than compressed natural gas. Therefore, by volume, the energy density of liquefied natural gas is 2.4 times greater than compressed natural gas, or 60% of diesel fuel. This means liquefied natural gases can be transported over longer distances where pipelines no longer exist, which limits natural gas transportation.
Oil-based products have been used for centuries as a source of light, heat, and energy. The reason behind this is because oil products have a high chemical energy that is easily released, generally by applying a little light and heat of our own. Crude oil is also relatively easy to find because of what it is made out of, dead things. Another reason crude oil is so widely used is because the refining process is easily scaled. You can have a lot of oil in a small area and not necessarily increase the probability of disaster. When it comes to oil-based products, the only way you're going to have something explode is due to the heat and pressure of the air. One of the main sections of crude oil use is liquid petroleum gas, more commonly known as LPGs. When speaking about LPGs, you're generally referring to propane and butane. Propane and butane are used in everyday heating and cooking. Propane can be used for gas grills, industrial vehicles like forklifts and Zambonis, as well as being used as a refrigerant. Butane can be used as an aerosol solution, as well as in handheld lighters. While they can both be used for the same purposes, each of them shine in a different way. Propane is easier to use and store, while butane is cheaper and produces 12% more energy when compared to propane. Another main use for oil is gas, also known as petrol, gasoline, or diesel. Both gasoline and diesel are made of varying hydrocarbons, but they both achieve the same result. They convert chemical energy into mechanical energy by using controlled ignition of said petrochemicals. They do this in two distinct ways. Gasoline uses a spark from a spark plug to ignite the chemical and cause a rapid expansion of air, which extends the piston and forces the gas out towards the exhaust. This creates a loop. The previous extension of the piston compresses and sets up for another ignition. Diesel uses a similar process, but rather than using spark plugs, it uses the chemical volatility. By using the heat generated by the compression of the piston to spark the next set of combustion. They both achieve the same result, but they do it in completely different ways. Gasoline and diesel are generally used for transportation, but can also be used to create power where otherwise it would not be able to be generated. Kerosene can and has been used as both a heating and lighting fuel. In the past, kerosene has been used in lamps to light the way. Today, it has been phased out of general use but can be used in disaster relief zones as well as by the societies that are separated from the norm. It can also be used as a fuel source for cooking and works exceptionally well in places where the temperature is low. Kerosene is also a main ingredient in jet fuel, but it needs to be in a higher concentration than what is sold on the commercial market. Lastly, kerosene is used as a cleaner and has been known to break down sticky and waxy substances easily, and afterwards evaporating almost completely. Many of the different petrochemicals used in power can be used in the same purposes, but generally they have a few things going for them that the others don't have. Some of the differences include the number of hydrocarbons used, how they react, how reactive they are, and how they react to different things. But they all have some things in common. They all produce light and heat when they react, and they all have a very high chemical energy, and none of them are super volatile. This allows for easy use on the commercial market.
What can you make out of oil? Background information. Most people have no idea of the tremendous number of common items produced from oil. Many people associate gasoline or diesel fuel with crude oil, but not the huge number of products that are used every day. The item produced from crude oil, scientists have identified at least 500,000 different uses of oil. These activities allow students to discover common products that are made from crude oil and to develop ideas on the importance of petrochemical products. Fuel, the most obvious example on this list, but justifies number one. The, com- the combined sources of gasoline, diesel, and jet fuel account for around 72% of petroleum con- consumption. The petroleum refinery process is complex, and these types of fuel may chemically differ by only the slightest degree. Despite this, different types of fuel can vary greatly in their physical properties and attributes, although they are essentially used for the same purpose. Plastic. Nearly all plastic are made from petrochemical. And plastic, needles to say is obviously everywhere. If you look around, you'll find that a great deal of our things are made, at least partly, with plastic. From your iPod to the bottles of Mountain Dew you're drinking, plastic forms a bigger part of our daily lives than our own mother. Annually, roughly 4 to 5% of total U.S. petroleum consumption is dedicated to the manufacture of plastic products. Food. No matter how organic you like your food, it's hard to find food that hasn't been touched by the oil industry to some degree. Petroleum byproducts are used in many synthetic fertilizers and pesticides. The use of petrochemical is also whispered into food preservation, flavoring, and coloring. Oil helps the agriculture industry produce more food and keep it fresh for longer. It also helps to pollute the atmosphere. Petroleum base are incidentally also found in your chewing gum. A difficult truth to swallow if I ever taste it. Medicine. Many of today's medication are derived from benzene, and benzene is a term is derived from petroleum. Almost all over almost all over-the-counter pain medications such as aspirin are based on petrochemical. Petroleum-based products are used extensively in homeopathic. Some have related to rise in petroleum engineering to raise from modern medicine. Other uses: one 42-gallon barrel of oil creates 19.4 gallons of gasoline. The rest is used to make things like ink, floor wax, boats, sweaters, bicycle tires, sport cars, body nail polish, fishing rod, dresses, tires, golf ball, perfume, dishwater parts, toolbox, shoe polish, motorcycle helmets, transparent tape, CDs, players, curtains, vitamin capsule, dashboards, deodorant, purses, soap, shoes, football player, and basketballs. Americans consume petroleum products at a rate of 3.5 gallons of oil and more than 250 cubic feet of natural gas per each day. But as shown here, petroleum is not just used for fuel.